Now we're going to explore the last two aspects of our NMR spectrum, integration, which is going to be 16.6, and then we'll do 16.7, which is multiplicity. So for integration, if we take the area underneath a signal, this will correspond to the number of protons that give rise to the signal. Now the numbers only have meaning when compared to one another. If we look here at this NMR spectrum, we can see the integrations in red. These integrations are shown as step curves. Now, although the numbers are not exact, we can see that the peaks are in a ratio of 2 to 3 to 3 to 2. Now, these numbers are only relative. What this means is that there may not be just 2, 3, 3, and 2 for a total of 10 protons. There could be 20 protons. Okay, so this is just relative values. Typically you can use either the molecular formula or the multiplicity, which we have not discussed yet, to assess the actual number of protons. Remember, when you look at integration values, to be aware of symmetry. We are going to practice interpreting NMR spectra, and it will allow you to make more sense of the integration values. Now let's explore 16.7, which has to do with multiplicity. The multiplicity is defined by the number of peaks in a given signal. It gives us information about neighboring hydrogens. This is very important to remember. The chemical shift and the integration gives us information about a given hydrogen. The multiplicity will give us information about the neighboring hydrogens. Please keep this in mind. So a singlet has 1 peak, a doublet has 2, a triplet has 3, a quartet, quintet, sextet, and septet, so on. We're not really going to deal with well-defined septets. Usually past quintet, we'll call those multiplets. And the reason is that the nice splitting pattern is very difficult to obtain with an instrument that you'll see in an organic chemistry lab. A signal's splitting is a result of the magnetic effects of neighboring protons. So, we have HA, and it can feel the magnetic field of HB. When you apply the magnetic field, some of HB will align and be in the alpha state, and other HB hydrogens will not align and be in the beta state. So, we can have HA and HB both be aligned. Okay. Or we can have HA aligned and HB not aligned, and as a result, the signal is split into 2 because it takes a slightly different delta E depending upon the spin states of HA and HB. Keep in mind, so remember, that chemically inequivalent hydrogens split each other. So now we're going to look at a more complicated case where HA is next to 2 hydrogens. Now remember that we can have the spins either aligned or against B0, the applied field. So if both HBs are aligned, we have one possibility. We can have one aligned and one not aligned, and we can have both against. So that this way, when they combine with HA, the signal is split into 3. And we see this triplet here. Now you can see the intensity of the center peak is almost double the intensity of the outer peaks. And this is because there are 2 different possibilities for that particular energy. So remember that each peak that we see corresponds to a delta E, the resonance frequency. When we look at splitting, a pattern emerges, and this pattern is the n+1 rule. And so what this means is that if n equals the number of neighboring hydrogens, then the splitting or the multiplicity will be n plus 1. Two things that we need to remember. Again, I stated this previously. Equivalent protons do not split each other. And 2, splitting is most commonly observed over small distances. What this means is that for our purposes, we are going to look at splitting with the nearest neighbor. So 1 bond away. And we'll practice looking at splitting patterns when we practice drawing and interpreting NMR spectra. The next thing that I want to look at in 16.7 is the coupling constant. When splitting occurs, the distance between the peaks of the multiplet is called the coupling constant. Or J value. Neighboring protons always split each other with equivalent J values. And I'll give you an example on the next slide. If we look at the spectrum here, or this portion of the spectrum, we can see that HA is split into a quartet because there's 3 hydrogens on the adjacent proton plus 1 that equals 4. HB is split into a triplet because on the adjacent carbon there are 2 hydrogens plus 1 equals 3. Now, because these hydrogens split each other, the coupling constant is the same, so that the distance between the peaks of the multiplet will be the same. And so this also confirms that carbon with HA is adjacent to the carbon with the HB protons. So this is another element that you can look at in order to determine connectivity. There are some common patterns to be aware of. in NMR. So typically an ethyl group will appear in an NMR spectrum as a quartet and a triplet, where the quartet integrates for 2 hydrogens and the triplet integrates for 3. And remember, for it to be an alpha group, the J values need to be the same. If you are not given J values, you can do this by inspection of the spectra. Another thing to be aware of is a terse butyl group. Usually it's a singlet. And the reason why it's a singlet is because there are no hydrogens on the carbon that are attached. All the methyl groups are equivalent. So you get a singlet that integrates to be 9 hydrogens. We're not going to worry about complex splitting patterns. I do want to address protons that lack splitting. So typically an OH hydrogen will appear as a singlet. So if we just take the example of ethanol, if we were to look at the hydrogen attached to the oxygen, you would say, based upon the N+1 rule, that there are 2 hydrogens on the adjacent atom. 2 plus 1 equals 3. That this hydrogen should be split as a triplet. But in fact, it will appear as a singlet. The reason is that this H is readily exchangeable, and as a result, the signal averages to a singlet. So remember that OH protons do not show splitting typically. In addition, an aldehyde proton usually appears as a singlet. This aldehyde proton, the coupling constant is very weak. As a result, it will appear as a singlet. And it has a very distinct chemical shift near 10 ppm. Alright, let's practice drawing the expected proton NMR spectrum for certain compounds. So let's start with the following compound. Now, the hydrogens are not drawn in, but you should see there is no symmetry. If we count, we should have 2, 4, 6, 8. 8 hydrogens in total. Now, so the integration should equal 8. This does not mean that we have 8 signals. What you should see is that we are going to have A, B, C, and D. We are going to have 4 signals in our NMR spectrum. Now, let's start with A. We're next to an oxygen, and this is an oxygen of an ester. So it's a CH2 group, which typically is around 1.2 ppm. We're going to add 3 ppm, so the signal should be around 4.2 ppm. So that would be our chemical shift. Now let's look at the splitting. HA protons have 2 hydrogens on the nearest carbon. So 2 plus 1 equals 3. So HA should be split as a triplet. It will integrate for a value of 2. Now let's look at HB. HB is a CH2, so the chemical shift will be around 1.2 ppm. Maybe it will be a little bit further downfield because of its proximity to the oxygen there. Now, if we look at HB, okay, HB has 2 hydrogens here from HA and 2 hydrogens here from HC. So the splitting will be 4 plus 1 equals 5. So it will be split into a quintet. And again should integrate for 2 hydrogens. Now I'm going to just write up here. So for HC, okay, again HC is a CH2. It will be around 1.2 ppm. Its chemical shift will be different from the chemical shift of HB, because now HC is closer in proximity to the carbonyl. HC will also be split as a quintet. So HC will also be split as a quintet and will integrate for 2 hydrogens. Finally, if we come to HD, okay, it's next to a carbonyl, so it's a CH2. It's 1.2 ppm. For the carbonyl, we're going to add 1. So the chemical shift will be around 2.2 ppm. Now, HD, there are only 2 neighbors which correspond to HC, so the splitting will be a triplet. And the integration will be 2 hydrogens. So I'd like you to practice that skill of drawing NMR spectra based upon a given structure. Now what I would like to address is 16.10 and how we analyze a proton NMR, and the steps that we're going to follow in our analysis. The first thing that you want to do, if given a molecular formula what you want to do is you want to calculate the degrees of unsaturation. Now the book talks about the hydrogen deficiency index. If you want to go ahead and do it that way, you're more than welcome to. I'm going to present on how to do it by degrees of unsaturation. And this will give you the total number of double bonds and or rings. And the way we do this is 2 plus 2 times the number of carbons minus the number of hydrogens minus the number of halogens plus the number of nitrogens, all divided by 2. Typically, when you have a large number, there's an aromatic ring, because if you look at an aromatic ring, you have 4 degrees of unsaturation right there. 1 ring and 3 double bonds. The next thing you want to do is look at the integration and see if there's any symmetry. And again, if you have the molecular formula, this will be relatively easy to assess. Next, you're going to look at the chemical shift. The integration and the multiplicity or splitting, and draw fragments. And I'll show you what I mean by this. And then last, you're going to assemble the fragments. If you love puzzles and logic, you will love solving NMR problems. Let's look at 16.54 in your text. So 16.54 says that we have a compound that has a molecular formula of C4H6O4. We have a broad IR signal between 2500 and 3600 wave numbers. In addition, we have 2 signals in our proton NMR. We're going to have a singlet at 12.1 ppm, and we are going to have a singlet at 2.4 ppm. Okay, and they both integrate for 1 hydrogen. Now we know that this is not the case, okay, that we're going to have to, this one has a relative integration of 2. We have 6 hydrogens here, so we have to do some kind of multiplication. Alright, so let's determine the degrees of unsaturation. That's step number 1. Okay, so it's 2 plus 2 times 4 minus 6 all divided by 2. So we have 10 minus 6 equals 4. So we have 2 degrees of unsaturation. Now this is very particular. This, which you'll learn from experience, typically indicates a carboxylic acid, hydrogen. Okay? Now, given this piece of information, we can corroborate this, that we have a broad peak, which could be the OH peak. Okay? So let's start working with the fragments. Now, again, we have 6 hydrogens, so there's got to be some type of symmetry here. Okay, and I can tell this by looking at the integration and the molecular formula. So, I most likely will have 2 carboxylic acids, one on either end of the molecule. Now, this already takes care of my 2 degrees of unsaturation, because now I have 2 double bonds. And so we have to figure out what the rest of the connectivity is. Alright, it also takes care of 2 carbons, so I have 2 carbons left. 1, 2. Okay, obviously, okay, they're not going to just be, oh wait a minute, no. Alright, sorry, not so obviously. Alright, so you can see here I connected the carboxylic acids by 2 carbons. And you can see that they're CH2s. Now, the signal is split as a singlet because this molecule is completely symmetric. And if you remember, equivalent hydrogens do not couple each other. So these are all equivalent, so there will be no coupling, so the signal will appear as a singlet. Okay? And again, if we look, this will integrate to be 2. This will integrate to be 1. So let's double this. Let's times this by 2, times this by 2. We get a ratio of 2 to 4. Here we have our 6 hydrogens. So just to redraw the structure for you. This is our structure. So we're going to do lots of examples in class on how to solve NMR problems. This is going to conclude our discussion of proton NMR.